Hello and welcome to Team Designated BR2's Balancing Robot project video for Clemson University Class ECE 4960 instructed by Richard Groff. Our team consisting of, from left to right, Brennan Van Nest, Brandy Cato, Mindy Ernest, William Sparks, and Chad Bell. Our goal for this project was to make a two-wheel balancing robot that autonomously corrects itself based on velocity and angle readings recorded by our IMU. Our project had several goals we were looking to obtain. Firstly, forward and backwards movement with right or left deviations. Also, our project had to rotate in place, right or left. Other guidelines for this project were for our robot to climb up ramps along with traversing an obstacle course in a timely manner following TATE guidelines laid out on the floor. We, as a group, had 3 milestones we wanted to complete in a timely manner. Our first milestone was to get our frame built and get motor and IMU tracking working. Our second milestone was to be able to balance properly, and lastly was to finally incorporate the movement as described before. Our biggest problem when designing, building, and coding our robot was proper hardware configuration, as our H-bridge gave us a lot of problems early on until we finally replaced it with a new one. The special hardware used on this project was a TIVA microcontroller, the main controller of our project incorporating our controls, an IMU allowing us to record velocity and angle measurements, a motor encoder to drive our motors, an H-bridge allowing us to reverse our voltage to our motors. Also, a Bluetooth chip was used, allowing for a wireless communication to our robot. Lastly, an analog camera and transmitter allowed us to operate our robot remotely without being present. The basis of how our robot functions is simple. To allow for congruent movement, we coded our robot to have a main wheel, allowing for our other wheel to track and respond to the main. We placed our IMU at the center mass to properly record our velocity and angle measurements. To balance our robot, our group had to take 2 considerations into account. Firstly is the velocity of our wheels, due to the fact that the quicker your wheels move, the more torque you have to apply to your wheels to stabilize your robot. And lastly, the angle of the robot was considered in our PD controller, which compares the current angle to the desired angle, which was 180 degrees. Basically, the more your robot tilts, the more your controller will need to adjust. We incorporated these 2 parameters into our control system, incorporated 2 feedback loops for them, and with a little tweaking of our feedback loop, stability occurred. Thank you, we hope you enjoyed watching this video, and hopefully you learned something new. This project was really fun for us to design and build. Thank you and have a good day.